So we're here for a solar eclipse, obviously, correct? Who's excited about that on Monday? I know I am. In all honesty, we went to a similar event in Oregon in 2017, and we got done watching that, and I turned to my wife and I was like, I can't wait for 2024. So I'm excited about this. But before we get started on what science or what solar eclipses tell us about God, I'm curious, what have we actually learned from solar eclipses? Take a little audience survey here. Does anybody know something we have learned from a solar eclipse? We'll go right here.
Confirmation of the theory of relativity.
Confirmation of the theory of relativity. And do you remember when that solar eclipse actually happened, perchance? Can anybody help her out? 1919, that is correct. That's and what was going on there is that during the solar eclipse, you're actually able to see stars behind the sun. And what general relativity said is that space and time are not space and time. They're space-time and mass warped space-time, and you can actually see the light bend, and so the stars were in a different position. And so that was one of the first confirmations of the theory of general relativity. Yes, over here. What else have we learned? You believe they discovered helium. That is correct. Do you know when they did that?
No.
That's all right. I'll tell you later anyway. What else have we learned through a solar eclipse?
The Earth is round.
We've learned the Earth is round. That is a good point. Yes, we have. That one happened a while ago, but yeah, no, that's... That God controls everything. That's right. We need a little bit more detail to get into that, but that is correct. Yes, over here, Ross. We can date past events. Did we learn that from the eclipses? Because I agree with you, but I think that's a different point than what I'm asking. Okay. Yes?
I think we discovered the corona through eclipses.
We did discover the corona through eclipses because it's really hard to see the corona unless you have an eclipse or you have pretty sophisticated instrumentation. What else? Well, good. I'm glad I decided to start my talk off this way because my talk starts off, what did we learn through solar eclipses? And you actually caught quite a bit of it. One of the first things we discovered are actually solar prominences. And these are the places where the sun actually has these big arcs and filaments of stuff that come off. And the first recorded mention of that was actually in the Russian Chronicle of Novgorod, and it's in the Laurentian Codex, and it was an eclipse back in May 1st, 1185. Somebody had written it down, and during the eclipse, they saw these flame-like tongues of live embers. I think that's far more poetic than I ever would have put it. And the challenge, or the reason why these were first discovered then, is that when you look at the sun, if you haven't noticed, the sun is really, really bright. And if you're trying to look at stuff that is dim right around it, it's very hard to see. In fact, what you'll find during the eclipse is that there are stars and planets up in the sky right now. Well, cloudy, you can't see them because they're cloudy right now, but if it weren't cloudy, you would be able to see them, except the light of the sun is just drowning them out. And so the eclipse blocks the light from the sun so that you can see these dimmer events. And so one of these are these solar prominences. Notice it was 1185. It wasn't until 1860 that they were actually photographed. And we can tell you this is not an actual photograph, it is an actual photograph, not from 1860. A little more recent than that. But in about 8 years later, these were all during eclipses where it was photographed. 8 years later, they discovered that these flame-like tongues of live embers were actually gaseous, and that they're not some solid thing that is protruding from that. So we learned a lot about solar prominences. You're correct. In here we saw the solar corona during an eclipse, and if we get to see the eclipse, you'll see it just stands out once the eclipse happens. But during that 1968 eclipse, where we figured out that these were gaseous filaments coming up, we also learned something else very interesting, and that was that this new element that we had never seen, actually, we found it on the sun first. And we found it helium. It was that same August 18, 1868 eclipse was where we found helium. And there was this other new element. It was called coronium. And I'll explain kind of what they were seeing when they do that. But it was this bright green light. It was thought to be a new element. But it turned out after some study, what we realized is that it's not actually a new element, but iron, that means it's got 26 protons, 26 electrons around it. This line that they discovered actually requires that the iron has had 10 electrons kicked off of it. So what it means is that it's got to be in a really, really hot environment. It's got to be nearly over 1 million degrees Celsius for that to happen. And so these lines they're seeing were not a new element, but an element in such an exotic state that it had never been seen before. And then one that I think is very cool, and you're going to see why as I go through my talk here, is that cosmic rays were actually discovered. They weren't discovered during an eclipse. I'm cheating a little bit there. They were actually discovered because there was this guy named Victor Hess who noticed that there were these charged particles hitting on the ground, and they thought maybe they're coming up from the Earth. And so that's what they're saying. They thought, okay, let's get up in a balloon. And so they tried measuring it at the top of the Eiffel Tower. Turns out there was a little bit less at the top of the Eiffel Tower. And so they thought, okay, that's actually coming from the ground. But he actually got in a balloon, and it actually built really good instrumentation so that they could measure it more definitively, and then took this instrumentation up in a balloon and found out that up to about 1 kilometer it decreases, but then above 1 kilometer it increases, which means that it's coming from outer space. And they didn't know exactly where they were coming from. So Victor Hess, in his balloon, actually took it up in April 17, 1912, which is another solar eclipse, and found that, lo and behold, even when the sun was eclipsed, you're still getting these cosmic rays. So it can't be coming primarily from the sun, because if that were true, the moon would have blocked it out. Because just in case you're not aware of what a solar eclipse is, we've got the sun. So we'll put the sun in the middle here. The Earth revolves around the sun. The moon revolves around the Earth. And on occasion, turns out that the plane that the Earth goes around the sun and the plane that the moon goes around the Earth are not the same, but twice a year they line up. And where they line up, occasionally you'll have the sun, and if you've got the Earth here and the moon out here, the Earth blocks all the light from the sun from hitting the moon, and so the moon goes dark, and everybody that can see the moon sees a lunar eclipse. And now if you flip it around to where the moon is over on the other side, sometimes the sun's light is blocked by the moon, and the moon casts a shadow on the Earth. And it's very rare for a given spot on the Earth to see a solar eclipse. It happens on the order of every 400 years, if you want to stay in one place. You're very fortunate, assuming we get good weather on Monday. The last solar eclipse in the United States was 2017. Before that, one that had gone all the way across the United States was 99 years before that. If you miss the one on Monday, we have to wait till 2044. So these are not particularly rare in any given place, but they are a very common occurrence. It's just being able to see a solar eclipse is kind of unusual. So I like this idea that Victor Hess up there using his balloon and figuring out that the cosmic rays are not coming from the sun. That was a cool discovery. But what I want to do now is, so this is some of the things so we got general relativity is confirmed, we found helium, we found new elements that show that the corona is there, we got solar prominences. All of these things could not have been learned unless we had solar eclipses. But what I think, beyond just the cool science that it demonstrates, is that when you probe into that in more detail, you actually learn about who God is himself. And let me go dig into some of the details, because it's the details of how this comes out that I think illuminate or reveal who God is. And so let's go look a little bit more closely at this discovery of helium. Now, everybody familiar with what a rainbow is? So you've got visible light, you've got red light, and I'm going to switch it right to left here. You're just going to have to get used to it. Even on my slides, it'll switch back and forth, just because nobody ever plots the same thing the same way twice. But you've got red wavelengths, which are about 700 nanometers. That's 700 billionths of a meter. Up to blue wavelengths, which are about 400 nanometers, 400 billionths of a meter. And everywhere in between, you've got the spectrum: red, orange, yellow, green, blue, indigo, violet. Roy G. Biv, for those who were in high school when I was in high school. We got rid of the indigo, so now it's just Roy G. Biv. But this is what you would see if you go out and split the sun's light into its component wavelengths. Now, our eyes are not sensitive to see all of this. We have to get some cool instrumentation that allows us to see. But what you'll notice, the bottom is, here's the intensity of the light you'll see. But if you look at it on the top, you'll notice that there are these bands where there's no light. And why that is that the light that's coming from the sun is pretty much even spectrum all the way across, but as it comes up through the atmosphere, there are these elements, and these elements will absorb specific wavelengths of light. And what you're seeing there, you can see some of those, like, that there's a big old broad line there right in the middle of the yellow. That's neutral sodium. There's hydrogen is one of the red lines that's gone there. Some of that is from oxygen in the Earth's atmosphere. So this is what you would see. Why I put all that up there is that we can actually go take each element and look and say, what are the spectrum that comes from that particular element? Now, in an eclipse, we're blocking out all the light from the sun. So we're not going to see this. What we're going to see is the elements that are giving off the light. And so if you take this same type of picture during an eclipse, you get something more like this, just right as it's coming out of the eclipse. You see there's this big bright red line, there's this yellow line, there's a kind of violet line and a whole bunch more violet lines, a whole bunch of green. You can see all these little lines in there. Well, as astronomers and scientists were saying, okay, what are these elements? Well, the first one, what's the sun made dominantly of? Hydrogen, we know that. And so if you go ask, well, here are the spectral lines of hydrogen. And this is a really cool 8th grade science fair project where you can they've got these machines that will take a tube of hydrogen and you can pass a current through it and it will glow, and then you take a little grating which has a whole bunch of lines on it, and as it shines through, the light will spread out, the different wavelengths will spread out, and you can project it on a wall, and then you can measure what the wavelengths are and you can figure out what the splittings of those are, and that gives you information on which sort of transitions they're making in the energy levels of hydrogen. At least that's what I learned when I did it. It's a cool part of having a dad as a scientist. And so you look at hydrogen there, you can see the big red line, you can see the purple line over there. Okay, that lines up. But you got this big yellow line. What in the world is that? Well, we know that even back in the 1800s, we knew that sodium has this very yellow glow to it. And so we go out and say, all right, it's not hydrogen. There's this cool yellow line. Actually, it's that sodium line is 2 lines at 598 nanometers and 598.6 nanometers. And as try as they might, scientists could not get those yellow sodium lines to line up with what they see out coming from the sun. And the difference is it's 597. Now think about that. It's 1/1000th of a meter off of what we thought it might be. 1/1000th of a meter in terms of wavelength. And so we look, and lo and behold, we say, maybe there's a new element there. And so we go out and look, and we start looking around on the Earth, and lo and behold, we do find this, but eventually this line from this other element lines up perfectly with it. In fact, that's why this element helium is called helium, because it was found on the sun, which it's Helios. Helium is the name of the element, that's why we call it that. And after some careful analysis, back in the 1868, we discover it's helium. Now, what I find fascinating about this, we discover it we find the line in 1868. It was another 15 or 13 years before we even detected those lines anywhere on the Earth. And it was another, 1895, what's that, 27 years? So we discovered it on the sun, took us 27 years to find it on the Earth. I think that's pretty cool. When you think of what we learned through the eclipse and confirming general relativity, and when you look at the details, it's not just that we found helium on the sun, it's that our universe behaves so incredibly reliably that when we look at it, and it's 597, not 598, not 598.6, but 597, that means there's something new going on. Things have got to be very, very reliable and trustworthy. And in fact, this is what God says about himself when we read through scriptures. I mean, there's this passage from Jeremiah 33:25. Jeremiah, if you read that, that's not a particularly good time or a very pleasant picture of how Israel is painted in Jeremiah. But when God is prophesying, or Jeremiah is prophesying to the nation of Israel about God, he says, this is what the Lord says, if my covenant for day and night does not continue, and if I have not established the fixed patterns of heaven and earth, then I would reject the descendants of Jacob and David my servant, so as not to take from his descendants ruler over the descendants of Abraham, Isaac, and Jacob. Now, if you get that in there, there's a promise to Jacob that you will have a ruler. There's a promise to David that you will have a ruler. And who made that promise? It was God. And he's saying, look out at the way the heavens behave. They are so reliable. They're so consistent. Do you know why they're so reliable and so consistent? Because I'm the one who made it. I'm the one who upholds it. And I am immutable in my character. I don't change. And if you want to know how reliable I am, look at how the heavens behave. You can count on them. You can trust them. And so you can trust me as well. So not only is he reliable, though, I think there's something else we can learn. And there's a fairly well-known joke that, you've got the atheists and the skeptics, one of them standing there before God, and he's going, God, we kind of got the world figured out. You seem a little extraneous here. We can kind of take care of all this. We know how it all works. We're getting to where we can probably make universes. And so God talks about it. He goes, well, can you make a human? It's like, yeah, we're learning how to do that. We kind of got the DNA figured out, and we're going to be able to make humans. And it's like, well, okay. So God says, all right, let's just do a little experiment and see what's going on here. So why don't we try and make a human? And the skeptic, the atheist goes over there and goes, okay, well, I'll go first. So he goes over there and he starts picking up some dirt and fashioning it. The guy goes, wait a second here. Go get your own dirt. Now, I say that because what I find is that I tend to have this impression that if I understand something, if I can write down and explain it, that's kind of the equivalent of being able to do it. And it's just not the case. So here we got a picture of a solar eclipse, fairly recent solar eclipse, but nonetheless, you see the solar prominences there, and they're flaring off, and we can actually, our instrumentation is better now. We can zoom in, and we see these big living fingers, flames of living embers flowing off of them. But this doesn't, we can do even better than this. We can go out, and we built telescopes that will allow us to go out and take, this is not AutoCAD or Photoshop. This is actual imagery from the sun, where the sun, it's a repeat of it. Yeah, exactly. It's the same one over and over, so it's not like it's just going off and off. Took me a while to figure that out. And if you look at it, these things eject at least 1 trillion pounds of mass. Anybody know what 1 trillion pounds is? You neither? I had to go look it up. You do? What weighs 1 trillion pounds?
600 billion kilograms.
600 billion kilograms.
The other way around.
You're right. It's 1.6 trillion kilograms. That helps you just like it helps me, right? So, but even more than that, it's not just 1 trillion pounds. It affects 1 trillion pounds at hundreds of miles per second. It's the most massive structure on the earth. Anyone care to make a guess? Great Wall of China. Do you know how long the Great Wall of China is? How many? I had to look it up. It's 13,000 miles. It weighs 1 billion pounds, or 100 billion pounds. So these solar prominences that give off stuff are ejecting something 10 times more massive than the Great Wall of China at hundreds of miles per second. I can describe it. There's no way I could accomplish it. Put all of us together, there's no way we could accomplish that. And so there's something different about being able to write the equations and understand why it happens, but it's a whole different measure to say we can make that happen. Another place where that shows up, talk about Victor Hess. He flew this balloon, and scientists are an odd lot, but I love the story of Victor Hess because he would get out in his balloon. Now, not the time frame there. This is early 1900s. April 7, 1912 is where he did the solar eclipse balloon flight. He would fly his balloon up to 5.3 kilometers, which is 17,000 feet for the rest of us. Now, what happens up at 17,000 feet? You ever hiked up at the top of a 17,000 foot mountain? You tend to not do very well. We have a telescope in Mauna Kea that is up at 17,000 feet. Most observers don't actually go up to the top because you tend to get headaches and you get sick. We're just not designed to be up at 17,000 feet by and large for most humanity. So this guy was doing that in a balloon. Pretty sure he was the only, maybe he took some friends up there with him, but maybe the only one up there. But so he finds these things called cosmic rays. And you're going to get to hear a little bit about cosmic rays because I like cosmic rays. So we now know that cosmic rays, I put look in quote, look the same over 10 orders of magnitude. That means 10 times 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 10 times, which is 10 billion if you put it all together, because that's what 10 to the 10 is. And I thought, it's just kind of interesting. What other things span 10 orders of magnitude? If you take a grain of sand, 10 orders of magnitude larger, you're the size of the Earth. If you take the Earth and the Sun, the distance between the Earth and the Sun, make it 10 billion times larger, you're now out at the Large Magellanic Clouds, which is another galaxy, closest galaxy. And if you take 1 second and make it 10 billion times larger, it's 300 years. So you go from 1 second to a lifetime. And when I mean they look the same, what you'll notice is that there's this very straight line that goes over that. So if I give you two numbers, you can basically characterize what the cosmic rays look like over 10 orders of magnitude. Now tell me two things that characterize your entire life. Can't do it, can you? Two things that characterize everything from a grain of sand to the size of the Earth. Taxes. Death in Texas. That's actually not bad, but that's not nearly as instructive to my talk, so I'm going to ignore that. Now, just to get a scale here, I've got this. The bottom scale there is in energy, and it's in electron volts, and it starts at 10 to the 9 and goes up to 10 to the 21. For your reference, so you understand a little bit of what that plot means, light here has an energy to it. Energy of that light has an energy of about 10. If you go to the doctor and you have a broken leg or broken arm or something and they take an x-ray, though that light has an energy of about 10,000. If you're working in a lab and you're exposed to an unusually large dose of gamma rays and turn into the Incredible Hulk, you now are exposed to gamma rays, light that has an energy of about 1 million, 10 to the 6. And if you go up even higher, you get 1,000 times larger, that's 10 to the 9. Now, why that's important is that you see it starts here at 10 to the 9. If you go way up at the top, if you were to take a detector that was 1 square meter in size, put it on the top of the atmosphere, you will get, in that 1 square meter detector, 1,000 cosmic rays every second. This is why we don't want to go out into space too much. One of the reasons why. Now, if you go down, they get much less frequent. So you get down there to this kind of bluish line, or the one in the purple there, that happens 1 per square meter every year. Down below that, it's 1 per square kilometer every year. But everybody who says, next time you hear somebody say, well, we're going to turn on a particle accelerator and we're going to make so much energy, we're going to create a black hole that's going to destroy the Earth. The most energetic particles we make in a particle accelerator are energies about 10 to the 12, maybe 10 to the 13. Nature repeatedly bombards Earth with particles that have energies 10 to the 13 to 10 to the 21. That's 100 million times more energetic than that. So if we haven't made a black hole that consumes the Earth, or if that hadn't happened already, it's not going to happen by anything we do. So the idea that humanity could make something that would consume the Earth is really kind of ludicrous, because God's already made things that are more powerful than that, and they haven't consumed the Earth. And I'm still not sure about this. I read this, but it seemed right when I put it up there. A little hard to say. If you go way down to the bottom end, that's an energy of about a flying mosquito. The other end is a tennis ball traveling 100 miles an hour. Now, mind you, these are not mosquitoes or tennis balls. These are protons that have the energy of a flying mosquito. Protons that have the energy of a tennis ball traveling 100 miles an hour. That's pretty impressive, you got to admit. So, not only is our universe reliable, and what we learn through eclipses point us to God's reliability, but it also just reminds us that God is really, really powerful. Is that right? It is He who made the earth by His power, who established the world by His wisdom, and by His understanding, He stretched out the heavens. When He utters His voice, there is a roar of waters in the heavens. He makes the clouds ascend from the end of the earth. He makes lightning for the rain and brings out the wind from the storehouses. He doesn't write down equations to describe it. He doesn't explain it in a physics class. He makes it happen. And so as cool as it is that we can understand what's going on, don't mistake that for having the power to make it happen, because that's who God is. One last thing that we also learn from solar eclipses is what is ultimately, now, we're looking at a solar eclipse, and what's fascinating is this incredibly bright object, basically all the light gets blocked out. But as you study this, so you go in and try, all right, light comes from the sun, and we think the surface of the sun's about 5,700 Kelvin. And if we go in a little more detail, you can actually do calculations and say, where the photons that actually come to Earth are generated because you're taking hydrogen and squeezing it together and making it into helium. That releases energy. And that energy now propagates to the earth. And when you take that and it makes a photon, and that photon travels for a little while, and then it hits another charged particle in the sun, and it gets bounced around. And you can calculate if that photon is made in the center or in the core where hydrogen fusion is going on, how long does it take to get to the edge of the sun? Anybody have a guess on what that is? It is a little less than 1 million years. It's on the order of 100,000 years. So think about that. Humanity's been around on the earth for about 100,000 years. All the light we're seeing coming from the sun was generated right about the time humanity originated. I don't know whether there's any theological significance to that. I just think it's kind of interesting. But once it does escape from the sun, it now comes towards the earth. And when it gets towards the earth, you get things like this. I would like to have taken that picture without the telephone pole in it. This isn't Jeff Zweerink draws something in Photoshop. This was looking down my street at the sunset. It just looks like the sky's on fire. I've seen this like 3 or 4 times in my life, and I was just fascinated with it. And sometimes when that light comes through the atmosphere, if it's a particular type of day where the sun's up in the sky and it's kind of a cool conditions up in the atmosphere, you get ice crystals up there, and as the light comes around that, it gets diffracted and you get this big ring up on the sky around the sun. And sometimes it makes it all the way down into the earth, and it's rain, and you can see the rainbows flowing out there. And it says something about the technology that I actually took all 3 of these pictures, and I'm not that good at photography. It's a reflection of who made all this. That God didn't have to make this world so beautiful, so impressive, so awesome, so majestic, but He did, because it reveals something about who He is. In fact, as we dig into that a little bit more, I think there's even something more in there to be had, because I talked about cosmic rays. So we've got these cosmic rays that have energies far beyond anything we can produce in the laboratory. And we have to ask the question, what in the world could produce those things? And you can show that in our galaxy, there's nothing capable of producing that. So something beyond our galaxy has to be what's doing that. And we know these objects out there are called active galaxies. And these are things that have not just massive black holes, not just really massive, but supermassive. That's actually the technical term for it, believe it or not. Supermassive black holes, billion times the mass of the sun, on the order of that range. And they have these huge jets which extend over millions of light years, and there's stuff in them moving at the speed of light, or very close to the speed of light. Unless you think I'm just making this up, this is an object called M87. It has a supermassive black hole that's roughly 1 trillion times the mass of the sun. You can see the jet of material coming out of it. That jet spans millions of light years. Think about just the duration it takes to form that in the first place. But there's this really cool, like I said, the stuff in that jet's moving at close to the speed of light. Astronomers think, hey, what would happen if we're not looking at it from the side, but we're kind of looking down that jet of material? Well, that stuff's moving towards us at close to the speed of light, and as photons come through there, they're going to bounce off of electrons that are moving close to the speed of light, and they're going to get boosted to incredibly high energies, and then they're going to hit other electrons and boost those to even more energies, and make protons and make stuff that are moving very, very, very fast that could make these cosmic rays that have these enormous energies. And what it takes to make something like that, this is an actual image, this isn't. But what we think takes to make these is that if you've got this massive black hole, supermassive black hole, as stuff condenses and falls towards it, it's going to make this disk of material that's rotating around very rapidly, and it's going to twist magnetic fields up, and it's going to make these huge jets pointing out of it, and as stars and stuff fall into there, they're going to get shredded apart and gobbled up, and emission's going to come out, and it's going to get funneled into these jets. And if you were to zoom in even further, again, this is not a real picture, you get in even further, there's going to be this black hole down there where it's just darkness. And you've got these jets coming out and swirling maps of material coming around it. And I didn't just make this up because a few years ago this is a radio picture, but we took an image of a black hole. This actually exists out there. And we know the creator who made it. He didn't have to make it that way, but this is the sort of universe he made, and that he's given us the tools to investigate. And as those cosmic rays now, as they come towards the Earth, that's a lot of energy. Something with that sort of energy comes plowing through people, it's going to cause a lot of damage. But what happens is as those things come, lo and behold, Earth is surrounded by an atmosphere. And not everything gets through that atmosphere. There are certain things that get through that atmosphere. Radio waves get through that atmosphere. That's why we listen to the radio and not the microwave. That's actually pretty funny now that I think about it. I did just make that up, believe it or not. Because microwaves don't make it through the atmosphere, or at least not nearly as efficiently. Radio waves do. Optical waves do there. Notice everything above optical waves, the X-rays, the gamma rays, and the more energetic gamma rays, they don't make it through the atmosphere. What they do is when they come down, these gamma rays hit the top of the atmosphere, and they deposit, and the cosmic rays as well, they deposit their energy into the top of the atmosphere, and it makes this big shower of particles. And these shower of particles have so much energy that they're moving faster than the speed of light in air. Not faster than the speed of light in a vacuum, but as you get into a medium, the speed of light slows down. And as these particles, they're moving faster than the speed of light in air, what happens when you move faster than the speed of sound? Get a sonic boom? What happens when you move faster than the speed of light? You get a light flash. And so that light flash is beamed at the ground, and it makes on the ground, it makes a pool of about 200 meters in diameter, lasts for 3 to 4 billionths of a second. And if you build telescopes, you can find that. That's what most of my scientific career has been doing, is working on stuff like that. What's interesting is that if you ask the question, how big of an area, how big on the sky is that shower, it's about half a degree. Take your thumb out, extend it, arm's length, that's half a degree. For every person, it's half a degree. If you're big, your arm's longer, so your thumb's further out. If you're short, you're smaller, thumb's closer in. That's half a degree. You know what else is half a degree on the sky? The sun. What else must be a half a degree on the sky if we're looking at a solar eclipse? A moon. So even though the sun is 400 times the diameter of the moon, it's 400 times further away, so they're all about half a degree. I don't know if there's any theological significance to that. Again, I just find it kind of fascinating. Because were it not for the atmosphere, the surface of the Earth would be exposed to all those cosmic rays. These are highly charged, highly energetic particles coming through all the time, and we would be exposed to those. You'd have to question whether the Earth was habitable or not. But our atmosphere, not only does it make it possible to get sunsets where the sky is on fire and rings of rainbows around the sun and just rainbows itself, but sometimes those charged particles, even as they're coming towards the Earth, they get funneled up and they hit the atmosphere and they make stuff like this. And so that kind of brings me to the final point of what we learn about God is he's not just reliable, he is reliable. He's not just powerful, but he is powerful. But he's also majestic. He's awesome. It says, bless the Lord, O my soul. Lord my God, you are very great. You are clothed with splendor and majesty, covering yourself with light as with a cloak, stretching out the heaven like a tent curtain. That not only has he made a universe that we can understand and predict and count on that reflect his reliability, that he's powerful enough to do that, but he's made it in a way that reflects his majesty and his splendor. And I find it fascinating that a lot of these same phenomena happen in the atmosphere, and God has seemed to put the universe together in such a way that we can't entirely understand it, but we have enough tools to kind of start moving that way. I find that interesting.